Okay, so the next question that we have on the menu today is asking us to solve each of the currents in each, or I guess every current in this circuit. And we want to use this by doing, we want to do this using a Kirchoff's laws. You know, Kirchoff's current laws, Kirchoff's circuit laws, they're both equally valid here. Okay, so let's draw this out, draw the circuit out so that we can be a little bit more clear. So here we have R1, and I'm going to assume that everything is just given in ohms. So 981 ohms for R1, which is connected like this to R2. And R2 is 325 ohms. Here we have a voltage source of 1.462 volts. So V1 is 1.462 volts. And here we have R3. That is 1475 ohms. 558 ohms here. Let's call that R4. Here we have, oh, here is R2, and that's R5. Whoops, my bad. So this is R5 and this is R2. R5 corresponds to 98.2 ohms and R2 corresponds to 325 ohms. Now between there we still have another voltage source like this. I prefer to draw my voltage sources like this because they cannot be confused with capacitors, because you know capacitors are just two parallel lines, and drawn batteries like that can be confusing sometimes. And we know that this is going to be 1.487 volts. Okay, so we have a couple different currents of interest. Let's label them. So here, let's say associated with R1, here we have I1. I have no idea where these directions are going, so well, that's not particularly important. Here, let's say this is I5, and here, let's call that I2, right? Because it's associated with R2. Okay, but first thing that we might want to do to make this a lot easier is you see that we have these three resistors. Let's simplify into one. Okay, so R1, we want to do, since they're in series, Req is equal to R2 plus R4 plus R3. R2 is going to be equal to 325 ohms plus R4, 558 ohms plus R3, 1475 ohms. Okay, let's ask our calculator, because you should not always trust yourself to do mental math. Plus 558 plus 1475. So here we have 2358 ohms. Okay, and that's pretty much as simple as we can get it. So just to quickly redraw it. Okay, let's just make that a little bit more clean. So here we still have I5. Nope, that's not I5, that's I1. Here we have I5, and here we have I2. Okay, so let's actually set up some equations that we know are going to be nice and convenient. So it's good to start with the nodes. So let's call this node A, and let's call this node B. Those are the main nodes of interest. So node A, we know that I1 plus I5 is equal to I2. So this is the incoming is equal to outgoing current. Okay. Yeah. So that'd be a great place to start, is that we know that, you know, if we have two of these currents, we can reason out the third one. Okay, so let's do some nodal, we can do some nodal analysis here. So we know we can call this ground. And we know that here is going to be a V1. So I5, we can calculate this with Ohm's law. So if we have pretty much, this is R5. This is V1 and this is A. We know that I5 is going to be equal to V equals IR, right? So this is with Ohm's law. I5 is going to be V1 minus VA over R5. Okay, we already know V1 and R5. We just need VA. That's what we don't know right now. Okay, so given that we have B as ground, R1, so let's do this with R1. We'll have VB equals 0 volts, ground. We want to say that this is R1 and this is VA. So we know here that 0 minus VA over R1 is equal to I1. Or we can just say negative VA over R1. The direction that we draw these currents doesn't really matter as long as we keep the directions constant on our diagram, so that our final calculations is going to agree with our diagram. Okay, but this will be our calculation for I1 given another Ohm's law situation. Okay, so now here, what we have here is, let's call this node V2 plus a VA, right? Because this is just a VA, but one voltage source over, we're adding V2 to it. So if we look at our REQ, Ohm's law, we know that here we have VA plus V2 REQ, and this goes over to 0 volts. So this goes to VB equals 0 volts equals ground. So we know that we had the current what the current we have in there? I think we had I2 is what we wrote, I2. Oh, and this was I1. So here, now that we have I2, using Ohm's law, we can calculate this as I2 is equal to VA plus V2 minus VB, but we know that that's 0, so we can just cross that out like that. All divided by REQ is equal to I2. Okay, so that will be our third equation here. Now remember at the beginning how we said that I1 plus I5 is equal to I2. So given that, the only variable of interest that we have left here, the only unknown here is VA. So if we put all of these three equations, if we sub those into here, I'll just rewrite it. We know that we had, what did we have originally? I1 plus I5 is equal to I2. Okay, I1 is equal to negative VA over R1. Okay, that came from here. I5 is V1 minus VA over R5. V1 minus VA over R5. Yep. Okay, that's I5. And for I2, we have is equal to VA plus V2 over REQ. Okay, now we want to pretty much, you see these terms, the middle, the ones to the right, we want to split those into two terms so that we can deal with them more easily. So VA R1 plus V1 over R5 minus VA over R5 is equal to VA over REQ plus V2 over REQ. Now we want to bring all VA terms to the same side. Okay, so let's bring them all to the right side and send this all the other terms to the left side. So we have V1 over R5, that's going to stay, minus V2 over REQ. It's going to be equal to VA over REQ plus VA over R1 plus VA over R5, and that's all. Okay, so on the right side we can factor out VA, so that'll be 1 over REQ plus 1 over R1 plus 1 over R5. Okay, so VA, if we isolate for that, we shall have V1 minus V1 over R5 minus V2 over REQ, all multiplied by 1 over REQ plus 1 over R1 plus 1 over R5, all inverse. And now we can sub in all of our numbers. So REQ is the only one that I don't have on the left side here. So REQ, we calculated that previously, and that is 2358. Ohms. Yeah, okay, so let's solve for VA. VA, we have V1 over R5. So V1, we had 1.462 volts divided by R5. Now R5 corresponds to 98.2. Minus V2, which was 1.487. And that was divided by REQ, which is 2358. Multiplied by, I guess, the parallel of all of those three resistors. Interesting. So this is 2358 plus 1 over R1. Who are you? 981. Plus 1 over R5, which is 98.2. Inverse. Our voltage here, VA, is now going to be something that we get from our calculator. Okay, so let's see. 1.462 divided by 98.2 minus 1.487 divided by 2358, and that is multiplied by 2358 inverse plus 981 inverse plus 98.2 inverse, and that whole thing inverse 1.226 volts. Okay, and that was our VA. Now the reason why VA is useful is because if we're given VA, we can easily calculate all of these currents individually. And honestly, we already have our equations up here. So summing these in, let's do I5 is equal to V1 minus VA over R5. V1 minus VA over R5. Okay, so V1 was 1.462 volts minus 1226 volts, all divided by R5, which was 98.2 ohms. Okay, so should be a positive number. 1.462 minus 1.1226. Oops. Did not write this correctly. Oops. 1.226 volts. Okay, so the result of this calculation is going to be 0.0024 amps, which corresponds to about 2.4 milliamps, which is precisely what we see on the diagram here. So that should be all good. Okay, so that was the calculation for I5 going upwards. And if we get the current I1, then we can just add that together with I5 to get I2, and that should all match up. So let's calculate I1. So we know that I1 is going to be negative VA over R. So I1 is equal to negative VA over R1, which is equal to negative 1.226 volts divided by R1, which we know is 981 ohms, and this shall give us 1.226 divided by 981 is 0.001249 amps, which is oops. We could also write that as 1.25, we can round a little bit, milliamps, which is exactly what we see on the diagram here. So that's we know that that is going to be good. Oh, it's a negative here. But originally we had our diagram here is I1 going into the branch, but we can keep it that way, and everything should work out. So we know that we had I1 plus I5 equals I2. So I1 plus I5 is equal to I2. I1, we just calculated that as negative 1.25 milliamps, plus I5, which we calculated as 2.4 milliamps. And doing this calculation, we get 2.4 minus 1.25 equals 1.15 milliamps, which is also exactly what we see on the diagram here. So, you know, these software tools are generally pretty good for calculating electric circuits. So we know that we have our I5, we calculated to be this, our I1, and this is our I2. Okay, so we found all the currents that we need, and yeah, that's all that we needed to know. So that would be a question complete. Here in the solutions, they went with a loop analysis. That's another completely valid way to handle electric circuits. As you get more practice, you'll see, you know, whatever suits your style better. I prefer the nodal analysis, but you know, it's perfectly valid to do the loop analysis. But either way, they can lead you to the same happy result. Okay, so the above solution is good. Is good. Comes to the same result with different perfectly valid strategy. Cool.